Okay, so moving on to test hint number 10. The degree of electronegativity differences in specific bonds.
Look it up.
Yeah. Okay, it's just subtracting this one.
Yeah, you get your periodic table out, and you turn it over to the side that's typically the back. My students call it the ugly side. And find that number. And find that electronegativity number, and determine what the difference is.
Right, just subtract it.
Right.
You did this when you were calculating percent ionic character.
Yes.
And you know what?
It was the numerator.
Right, right. And I think we gave him a pen cast on that too.
Yes.
So go back and watch the pen cast.
Yes, that was a good one you did.
Number 11.
11.
The test hint says.
An example of an atom or molecule that can have more than 8 valence electrons.
Now in this one, we will give you the chemical formula. Okay, but you should know that there's a couple atoms up there in that right corner of the periodic table that are perfectly okay with having more than 8 valence electrons.
Yeah, there are a couple that can do it, and if you take the time to look at the formulas that are on the test and count up the number of bonds that must be in this formula, you ought to be able to figure it out.
Right, yeah, look at how many things are attached.
Right. Number 12.
The number of electrons that can occupy a molecular bonding orbital. Oh my gosh, now we're calling them molecular orbitals.
Does it really matter?
What happened to the atomic orbitals?
How many electrons can be in any orbital?
2?
Does it matter if it's atomic or molecular?
I don't know, does it?
No, it's still 2.
No. 2 electrons in an orbital. Did it come from 2 different atoms or the same atom? Still 2 electrons.
Yeah, it's still going to be 2.
Okay, 13.
Number 13, how pi bonds are formed and what they are. This pretty much taxed my artistic ability to draw these
Pi bonds.
Yeah, these pi
I'm not
bonds.
really good at this.
No.
But
it's
try.
Yeah. In a nutshell, a pi bond is a second bond in a double bond that has to form around the bond axis because there's already a sigma bond in there because the sigma bond is a bond in which the electrons are right along the bond axis, directed between the 2 nuclei. And since there's already electrons in there, more electrons cannot pile into that space because electrons are negative and they all repel each other.
Well, and we know that only 2 can go in an orbital.
Yeah.
But they pull that close together.
Yeah.
Right?
Yeah, that space is very small. And you simply cannot put 4 electrons into this molecular orbital.
Right. Now these 2 carbon nuclei are moving closer together. And there's an unhybridized p orbital. So in this example, carbon hybridized 3 of its 4 orbitals and left 1 p orbital the same. So these like bump into each other, basically, and form that double bond. I like to show mine for my students is we overlap directly here to make that nice strong sigma bond. And when we do that p orbital, the p orbital
Very nice.
bumps into each other.
Right.
Okay? And this looks like kind of a mess, but when we draw it like a normal molecule.
What I did with my kids was I wrote it this way, that these clouds literally form a loop around the outside for these electrons to orbit this way.
Right. I like that. And, you know, in 2 dimensions on paper, when you're drawing just the Lewis structure, this mess is really just this.
Yes.
So we're talking about 1 direct overlap, and this other thing is this other bond. Okay.
There you go.
Where are we going?
We should be at 14, yes.
14. How the strength of sigma and pi bonds compare. Okay, I was kind of doing that with my fingers before. So I got my p orbital, and I got my hybridized s orbitals, and those can overlap, and I can really hook those together, and that's really strong. But, you know, the other things I can just kind of bump apart.
Yeah.
That second bond there, that pi bond, is not as strong as the direct overlap, because this is overlapping indirectly.
But even though your pi isn't very strong.
Right.
How does the strength of a single bond compare to the strength
Oh,
of a double bond?
well, I mean, a double is going to be stronger because you've got two bonds instead
Right.
of one.
Even though that pi bond isn't
Isn't
super tough, it's still a double bond. It's still, those two atoms are bonded twice.
And we know that because it takes a lot more energy to break apart.
Right. Exactly.
Okay. Are we ready? 15.
I'm ready. 15 is the shape of a methane molecule, VSEPR. You
Right.
have a central atom with 4 shared pairs,
Mm-hmm.
no unshared pairs.
Right.
Those bonding pairs of electrons are going to get as far apart from each other as possible, and that's 109.5 degrees, I believe.
Right. And that's our tetrahedron. This is all about tetrahedral geometry. All these molecules are trying to be in that tetrahedral shape.
Yeah.
You have drawn this a bazillion times.
Yes.
Look at transparency 29. You got 4 different versions of that in the back. This one, you know this.
Yes.
Alrighty, 16.
16.
Why bent molecules form according to VSEPR. VSEPR. Well, it's why any shaped molecule really forms according to VSEPR. But let's throw up our water. Well, that's not like
Yeah.
throw up our water, but let's draw our water. And we know that oxygen has 2 unshared pairs. And the unshared pairs, they take up a lot of space. I'm trying to find a cup of water here.
There you go.
I don't know if it'll be big enough for you guys to see, but here's a little bitty water molecule. And with this model, we've got hydrogens attached and looks like nothing on the other side, but it's actually unshared pairs. And those are in orbitals that crowd out everything else and pushes the hydrogen-oxygen-hydrogen bond down smaller. What's the angle?
107 point something? Or is it 104.7?
104 points.
104.7.
And, you know, all of those electrons want to repel each other because they're negative. And it's those unshared pairs on that center atom that are really determining the shape.
Yeah. They literally, they take up more space. We didn't just draw them this way
For fun.
just to fill up the board so you can see it from there. These unshared pairs literally take up more space. These bonded pairs are being attracted. Their motion is confined due to the attraction of this nucleus and this nucleus. They simply do not occupy as much space, so they don't exert as much repulsion.
Okay, number 17. The name of the hybridized orbitals in methane. Well, methane is carbon with 4 hydrogens attached.
Didn't we do
And
that before?
yeah, we did kind of. But you know what? They always get messed up with the fact that now we're giving them a real molecule,
Yeah.
as if it's any different than the other one.
Oh no, they're calling it by name.
Nothing. So we've got CH4, carbon with 4 hydrogens attached, or tetra, forms the tetrahedral shape. You did a nice drawing before where you had an s orbital, like the 2s, and 3 2p orbitals merging together, and we made that the 2 sp3.
sp3 hybrid. It's this s orbital and 3 p's. It's 4 orbitals.
Right, so that's why this has 4 places to bond. That's the kind of bonding, or hybridization in methane is also probably the most common.
Right.
Alrighty, number 18.
Number 18 is the possible shapes for molecules with a triple bond.
This one is so easy.
Yes.
Like, it can only be one thing. Right,
Yeah,
they made the
since-
strings and the
Yeah.
spheres.
And even the Lewis dot structures. You just don't have really any choices.
Should we tell them?
No.
Okay.
No. You're such a softie. Number 19, how to identify the most polar covalent bond from a list of examples.
You did this on, well, pretty much every lab that we did here. We're looking at that electronegativity difference again. Say we have HCl, okay? Is that polar? Not polar? have a positive end and a negative end of this molecule. Great simulations that we showed you, by the way. And this would be a polar bond, but we need to compare it to something else. So how about an H bond?
Dude, there's no comparison here.
Right. And what else?
We could do maybe, how about a HC bond?
An HC bond. Okay.
So now this is starting to look like a decent multiple choice question.
Right.
So, just eyeball, looking at these elements on the periodic table.
And what you know about the trends.
Right. Who's closest to fluorine? Fluorine's the most electronegative element on the entire periodic table. Who's closest to fluorine? Chlorine.
Fluorine is.
These three are all the same.
Are you sure?
Yeah.
Okay.
We're trying to make these questions workable for you.
Right.
So this one is going to be the most electronegative. This one is going to
Of
have
these choices.
the biggest difference from this one's electronegativity value.
Okay, so if we look at our model, can you slide our model in there, Mr. Sustin? Oops. Here's our model. And these represent shared pairs of electrons between two nuclei. The lower one is an example of this HH bond, where there's equal sharing. The upper model could represent either one of these. It's just a question of, in this particular test question, where is there the biggest difference in electronegativity? Look up the values on the back of your periodic table and subtract.